Faculty members of the university, researchers, scholars involved in the research being conducted here. And this is a relatively new research institute that we have, focusing on life under extreme conditions, as you will see during the day, and as Mira has already said, this is not a dead place in any way. So since we are a little behind schedule, I'll call immediately my colleague Dr. Mira Marcus, who is the academic coordinator of this research institute, in a way the driving spirit behind this initiative, research initiative of Tel Aviv University, apart from doing very many other things within the EU and Tel Aviv University's involvement in European programs, especially the Human Brain Project. But Mira, the microphone is yours.
Okay, thank you, Ranan, and I must say, you know, we are a family already, we know each other, that if Ranan wouldn't have stayed beyond all this, your visit, but also helping us at the university to move those new ventures, it wouldn't have happened, so thank you. And before starting, I want to invite Dudu Ben Shabbat, that is here, that is managing director of this wonderful place, actually brand new place. And I want to just invite him to welcome you for a minute before I start. So he's taking care every day of what you see here and everywhere. And that's later, because otherwise I wouldn't listen to the lectures. That's at the end.
I welcome you.
Thank you. So he's very sensitive as well. And
no, I'm not.
A very, very special place, and the only one place in the world, as I say, the lowest place on earth. I hope you felt a little bit of that when we went down. And what I told you about the submarine, that we really understand the way it was structured. And it has, as I said, some very good benefits to our health, but not only. The mud that unfortunately we won't have time for you to try, but it's antibacterial with minerals, again, with different, not only cosmetics and not only skins. And the last one is the water with all the minerals. So this rare combination, unlike anywhere else in the world, is a very special environment. And also, as we talked about the title of this center, and the reason of this center is for us to learn, to get a lesson from nature, and to see how do nature cope with this extreme condition, and how could you utilize or learn from this extreme condition for the better well-being from the broadband. And, you know, I told you, from a physical environment to culture, it was a really cradle of humanities, of the nature of humanities. And you can see just those that are quoted here. And we're looking on the special, unique places of this area. And there were even debates if, as a Jew, you can go into the water on Saturday, whether it's work or not working on Saturday because of the asphalt. So it's very interesting, the debate so many years ago, and I told you already about the perfume. So, you know, it was a very vivid area, and it was a pathways, and we know it through the history of very many troops and people from the beginning of humanities, and there were even some evidence of the first people that went through this area. And we won't have time to go, but I mentioned a little bit on the way of these special places that you should visit one day. in the area. But it also, you know, in some parallel research or parallel believers, I would say, some think that this area is really the center of the energy of the world. The big debate is only if it's in the water or up on the hill. So there is still debate, but they think that this is the center of the energy of the world.
High impact papers, because this is a very important area of research. Okay, so we are in the Dead Sea, and that's why I'm here to tell you about the connection to the Dead Sea and the microbiomes. So Mira already said that this area is unique in terms of salt, aerosol, UV, temperature, and we know it has many beneficial effects on the skin. Mira also told you that. Now, those extreme conditions have a tremendous influence on the skin. The question is, how are the microbiomes involved? So, do the conditions affect the diversity of the microbiomes, the composition, who's there, what do they do? And also, are the clinical benefits associated with the microbiomes? Because it's quite possible that there's a special microbiome adapted to this area, and maybe if we can do something with these microbiomes, we can change the ability of people, their skin, or even, as Mira wants to see, their nervous system or cognition. Okay. So I just want to show you that there's a basis for this wishful thinking, and this is I'll just show you one experiment that we did. We did that in Tel Aviv, and in Tel Aviv what we did is we wanted to see if a long exposure to the sea, the Mediterranean in this case, and the sun has an effect on the microbiome of the skin. So we took samples from lifeguards in May and in September to see what do the microbiomes of the skin look like. And this is the May microbiome, not all of it, just a little bit. You can see all these bacteria that were present on the lifeguards in May. And when we did the same in September, surprise, surprise, we have here 3 new bacteria that were not present in May. So we know that there's a very clear effect of the conditions on the skin microbiome. And I can tell you, for those who are more interested in biology, what is the control, you know, because for an experiment you have to have a group that is not exposed to the sea. And we got a group of people, I'll say it, for those of you who understand a bit, yeshiva bochers, you know, is people who are studying Talmud all day. They don't go out and they are wearing black things all over, so they don't see the sun ever. They go in early in the morning, they go in late, and we looked at the microbiomes of that. There was also change, but a completely different change, because probably the change there was due to the fact that they were there in the, you know, very hot clothes, not well conditioned. They did not go outside, and we have bacteria that are typical for sweat and for heat conditions of the skin. So we can see fantastic differences, and now of course we want to see what happens in the Dead Sea, exposure to the Dead Sea. So our plan is to study the effect of the Dead Sea on the composition and the diversity of the skin microbiome. We want to focus on healthy people, but also we want to look at psoriasis people. You know, psoriasis is a very unpleasant, not life-endangering, but it's an unpleasant disease, and clearly has to do with skin microbiomes. I am sure that we will see very clear differences there. And here is the best place to look at psoriasis patients, because they come from all over the world. They come from Germany. There are some people with psoriasis who spent the whole winter in Israel. and lots of people from all over the world, so they have different diets and different everything, and the only thing that's common is that they have psoriasis and sit in the Dead Sea. So it's a fantastic group to look at. And of course with this we want to understand better what affects the skin microbiomes, but also the long-term wish is maybe we can learn something that will help us to develop a microbiome-based therapy or help for people with skin diseases. So with this, I thank you.
The
old TV.
Yeah. Okay, now it's working. Now we've changed it. Okay, so welcome. As Mira said, when I ended my term as vice president, I decided to devote all my time to research, but I could not say no to Mira. But as a Lior, I think that I will find an interesting thing to do also in the Dead Sea and helping the Institute in general. So Eliora tried to convince you that everything is microbes. I will try to convince you that everything is molecules. Until recently I thought that everything is proteins and peptides. Now we think it's metabolites. Everything is self-assembly, as some of the people in the audience know. But we are...
יש לך את הפוינטר קדימה אחורה.
Okay. So, how did we get to molecules, small molecules, very, very small molecules? It's by trying to understand the most fundamental processes in nature. And the Dead Sea is really the place to think and be inspired of having the simplicity and the ability of simple things to form all the structures. Our approach, although not all of you are from the exact sciences, but I think it could be understood. Our approach is reductionist, minimalistic, non-biased, meaning we take complex modules that can form ordered structures by the process of self-assembly, self-organization of molecules to form ordered structures, and we cut it in a non-biased way, a reductionist approach to the smaller and smaller places, until quite recently our claim to fame was the ability of dipeptides, the shortest you can get with two amino acids that are joined together to form ordered structures, but later on we found that single amino acid, other metabolites can form ordered assemblies. Why is it interesting? It is interesting from both the biology point of view, technology point of view. We find very interesting properties when we get to structures that are formed by simple building blocks, mechanical properties, optical properties, piezoelectric properties, semiconductive, or physical properties that you can think of. We can find in the structures that are built by very simple building blocks. But as smart as we are, nature is even smarter. And we realize that our systematic reductionist approach many times leads to something that nature already revealed by the process of evolution. And one thing that I really like is this very vivid example in the case of guanine. Even if you are not in biology or chemistry, you know, guanine is one of the 4 nucleobases that build the DNA and RNA. A, C, T, G. G is the guanine. But guanine is also very interesting from the optical point of view. So, physical colors in fish, the ability of chameleons to change their color, reflectors in reptile eyes, all made by self-assembly of guanine nucleobases in an ordered, coordinated structure to form nanoscale ordered assemblies. And it is interesting for us to find this building block and find guanine and to be able to manipulate that structure. Another example of how nature probably time after time is getting into the same solution. So tapetum lucidum or tapeta lucida in plural is those reflectors, as I showed you earlier with the reptiles. It's made of guanine. For cats and dogs, these are made of also for biology, so it's quite simple molecules. In the case of the reflectors in cat eyes, it's made of riboflavin, vitamin B2. In the case of dogs, it's made of the simple amino acid, 16 amino acid coordinated with metal. And while cats and dogs are enemies in nature, they are quite close from the evolution point of view, but still, they are using different strategy. But lemurs, which are much closer to us as primates, are actually once again using the riboflavin. So the ability to use self-assembled structures was developed probably in an independent way along the evolution, and I think it's quite exciting and significant part of the work that we have now is related to metabolite self-assembly to form functional structures. And all is done by self-assembly. The ability for molecules to interact in non-covalent ways, there is not to change their properties and find ordered assemblies. Deborah knows this example. I swear to God, this is my regular slide. It's not especially for you, so please tell Sam. I think that it's fascinating what you can do with self-assembly. So, we and others study this extensively, and so this is what I show in more chemical, but I had to put it because of Deborah. In a more popular way, I'm trying to say that. Oh, did you take it?
Yes.
But this interaction, this what we call non-covalent interactions, are weak interactions, but yes, that's a small group. But put together, they could get the formation of quite stable assemblies, as in the case that I showed you with the different metabolites. So this is a little bit like the Gulliver travel to the world in our case. We need to define all the different small interactions that together, collectively, can form functional assemblies. And for many years, our claim to fame was a dipeptide, this very simple molecule that can form ordered assemblies, published in Science. It got quite a lot of attention, but when it was published in New York Times, got much more attention. So I realized that more people read the New York Times rather than Science magazine, and has many properties. Not only optical, this is mechanical properties, piezoelectric properties, semiconductive properties. Recently we finished many years of studying this peptide with this another science review on the semiconductivity. So these structures can really act as electronic component as we think about, and I think that this is really the future. Everything that we have around is electronics and semiconductors. But we are limited to what we have with the silicon and germanium semiconductivity. The future, as we see it, is in organic and even more importantly, biological semiconductors, and already there are various applications for such structures, for making sensors. Just move fast, just to give you a flavor of things that can be done with such structures. Making smart windows, super hydrophobic, so you can have the structures that are being cleaned by such assemblies. things that are not high-tech, but quite important for restoration of dental materials. And something that got a lot of attention is by being able to form structures that increase significantly the surface area of electrodes to make a fast charging batteries. And actually technology, luckily I was vice president, I didn't have the time to go into the running a company, but a company that took license from us is raised quite a lot of money trying to make new energy storage devices out of such structures. And now it's very popular around the world. So electric device, energy harvesting device made out of it. So all of this was with peptides, and until quite about 4 years ago, or 6 years, yeah, no, 6 years ago, if someone would ask me what is the minimal requirement to form ordered assembly, I would say dipeptide, which is quite simple, which can build structures with unique properties and others. And then we did a control which made us into all this world of metabolites as I started with. We asked whether a single amino acid can form ordered structures. And the answer should have been known, and then we would be the leaders of short peptides and end by that. But the nice thing is that when you do science, you can find new results. And we realized that single amino acid, in this case phenylalanine, which you may have heard the name if you consume diet drinks, can form well-ordered structures and also toxic one. And we find by then, by the understanding the ability of a simple single amino acid, as formed in the case of the eyes of the dog, to form ordered assemblies. We suggested a new mechanism to understand PKU, phenylketonuria, even if you don't well familiar with this disease. I guess that you saw this in the past on diet drinks. Contains phenylalanine, not for PKU patients. So this is a disease in which individual lack the enzyme that converts phenylalanine into tyrosine. It's a single mutation. And by understanding the ability of and then they have accumulation of phenylalanine, this amino acid in their blood. Then by understanding the ability of this structure to self-assemble, to form ordered structures, we understood something that was quite mysterious for many years. That is, what is the reason by which individual who have the accumulation of this amino acid have abnormalities, neuronal abnormalities, and this is probably to the nanostructures that are being formed. We demonstrated this ability, and then we realized, so this is the way that we moved in our reductionist, systematic non-biased. This is structures, large protein that perform all the structures. We moved to smaller one. We moved to dipeptides for many years. We moved to single amino acids, and now we're going back to medicine. There are many diseases in which you have accumulation of metabolites, and we provide a new mechanism of action for this. I will end with even a more provocative directions. As you see, we like technology, we like medicine, we like electronics. It was suggested for many years that the environment for the origin of life was hypersaline. And this is due to the fact that you can see what is known as salt-induced peptide synthesis. So you take amino acids, or chemistry 101, but I think you're vice president not for me. You take amino acids, the basis for proteins and peptides. In salt-induced conditions, you can get the formation of the structures. This goes well to what we suggested 13 years ago, but now got quite a lot of revival by other people, especially the Greek group at ETA, which is due to our understanding that very simple peptides can form all the structures. And the interactions between the nucleobases, like the guanine, but also adenine, uracil, cysteine, cytosine, with these structures, it may explain how everything started, because the prevailing hypothesis is the RNA hypothesis. RNA functional structures are much too complex to explain the early stage. We believe that it's peptide, maybe even metabolites at this stage. So this would be like Leilior presented their research proposal. This is our research proposal, okay? And we just discovered what was suggested by Leonardo da Vinci. Simplicity is the ultimate sophistication. We go to smaller and smaller structures. Okay. If somebody is interested in what is the hyperlink to my website. Now we don't have time. Yes, please.
So, my daughter knows more chemistry than I do, and I'm extremely, you're extremely distinguished scientist. You're trained in Israel. You spent some time at MIT, I understand.
Yes. You did.
Yeah. So a lot of us work on the international. And my question is, many of your teams look like they have some international character to them, like you have co-authors who are international and so on. What institutional arrangements on the part of the university make it possible to do world-leading science in Tel Aviv, for example, and to what extent do you need any assistance from a university's international office to make these things happen, or do you just find that because you're already a well-known scientist, you've studied in America, you've got colleagues all across the world, you don't really need us to make it happen? I ask for my own sake. I hear you. I think that Israel is, so now I will wear also my previous vice president hat. Israel and universities like Tel Aviv University, but same goes for Hebrew University. And that, I think that we have really very innovative science. When I was vice president, I used to say that we have Ivy League PIs with a good state university infrastructure. But really, both the PIs as well as the students, our best students are as good and sometimes are better than students at the most elite universities in the US. And the curriculum is very rigorous. You mentioned MIT. When I was a student at MIT, some physics undergraduate courses at Tel Aviv University were allowed for a PhD, was accepted as PhD level courses at MIT physics program. So I think the curriculum is also very, very stringent. And research is less expensive as compared to the US. The overhead is lower. We are now very much have the great benefit of getting funding from the European Commission. What we still need. My lab is very international. I have people from all around the world, but not from the US.
China, from India, from other places. I think that Israel could be quite attractive place, at least the leading labs in Israel, for somebody been doing a PhD in the US, come to Israel for a postdoc, and then can go back to the US or other place for top academic job. India Verma did his PhD at the Weizmann Institute in the 60s or 70s. He didn't inherit his scientific career.
Is there something preventing that from happening?
I don't know. I think it's for students from China and India, we have allocated fellowships, which makes it very attractive.
So in part it has to do with funding issues, but in part it has to do with a certain legitimacy, quote unquote, that can be achieved through institutional arrangement. So if a PhD student in any of the universities present here would know that his or her university has an institutional tie or relationship with Tel Aviv University, it would certainly make him or her consider the possibility of spending time here as something which is worthwhile.
I would add something.
But how would they get funding? How would they get funding?
No, the first issue I refer to was funding.
To get funding. I think that, and we see it many times, less from the US and more from Europe, because it's much easier to get funding for a graduate student to travel from Europe. They come to Israel, sometimes from really elite universities in Europe, Cambridge University, Oxford, ETH, and they realize that science in Israel is really high level. Sometimes I consider we have now a student in one of the affiliated labs of my larger group, coming from an elite university in Italy. So when they have the opportunity to come for a month or 2 months as graduate students, I think those graduate students realize that maybe, wow, it's even worthwhile to do postdoc in Israel.
Okay, I'm a simple seismologist, and when Mira asked me to give a talk here, I looked at the program and I realized that I'm just a seismologist, I'm not involved in education and online and international things. And then I realized that actually, yes, I've been thrust into that field and I'm trying to share it with you. So, okay, so basically seismology we deal with earthquakes, so I'll just go very quickly on the science and just to give you the background. We're in a very strange area. It's not a very known or seismically active region, but it has a lot of historical destruction, and my archaeological colleague knows a lot about it. You'll probably hear about this or other things later. So we have this kind of duality. It's not very active, so people don't feel earthquakes, and I'm certainly not aware of it, and that's because of the political situation, but it happens, and it has changed even the course of history significantly. Now, we also live in the region, seismologically is quite interesting. It's like a basin, so it basically works like an optic fiber. It concentrates all the energy and keeps it. So even a small earthquake, you feel it. And we have a history of good destruction. And you can see the other thing that's interesting that I've plotted here is that these are archaeological sites that are destroyed by earthquakes, and you can see that there is a selective destruction, and there is a definite connection with the Dead Sea. Now, the third challenge that we have when we do seismology in our area is that the Dead Sea Fault Zone runs here. I'm not going into detailed politics, but this is basically Israel, and this is Jordan. And you can see that as it is everywhere in the world, the Americans have their seismic network, the Canadians have it, and they don't overlap. Okay, so it's the same here, except that it's slightly more difficult because we don't exchange data, certainly not in real time. So when you want to do seismology, it's like you're seeing only the one side of the body, the lower part of the upper part. So we came with the idea that maybe we need to change that. Now I'll show you very quickly, and you probably know how we basically locate earthquake, which is something important for us. Is that we use many stations with a different time arrival, and knowing the structure of the subsurface, you can figure out where the earthquake is. But basically using information from many stations. Now, because of the situation in the Dead Sea, and because I was basically playing with other things, we came up with something which is a little different, which we call array seismology. So instead of just putting sensors here and there, we just, like within a football field, we just put many sensors. It's called an array. It's used in astrophysics and in a lot of other fields. We've not invented anything. We just took it in seismology and at a small scale. So what it does is that it basically empowers us. So instead of relying on the whole network and maybe on colleagues on the other side of the Dead Sea or in Mexico or wherever, we are alone, because with our little mini array, we can basically go and point towards the smoking gun for us an earthquake. Or it can be a blast, it can be fracking actually, for all that matters. Okay, so, but remember this, because for education, I will show you how it empowers us. Now, I'll just show you this little diagram. I hope it works, and if it doesn't, we'll gain time. No, it doesn't work. Anyway, I just wanted to show you how clever we are, but it doesn't matter. So, what we did is that we came to the situation that we set up a small, modest seismic network called Dead Sea Net. It's located here where the triangles are. So if you can see, some of them are on Israeli soil, some on Palestinian soil, and soil. So that the network, which is basically a cluster of mini arrays, is very special. First of all, maybe the least special thing, but for us it's important that in that region here, it's a part of the Dead Sea Fault. It's located the closest to about 8 million people. Okay, so it's a kind of significance, like going under the Los Angeles basin. Now it's the only trans-border seismic network, and in real time. The French with the Belgians and the Germans share seismic data, but they do locations once a day or something like this. Okay, so you understand that for earthquake, especially for early warning system, it's a little slow. So here we have transborder, and we share information in real time. Okay, so it's mini array based. We have true monitoring. Okay, low budget, and all the data, of course, is encrypted for reasons not only for the security of the region, but that it's easier to put sensors in somebody's garden if you can tell him that nobody will be able to monitor when he drives his car out or in and out of his driveway. Okay, so now the interesting thing is that, okay, we started to work with our colleagues actually there, and I know how strong Tel Aviv University and many universities work on interactions, and I'm very much for it. But everything that happened to us was chance. Okay, my Jordan colleague was the first Jordanian postdoc in Israel at Tel Aviv University, with the same age. We kind of run into each other, became very, very, very good friends. He's now the president of the biggest public university in Jordan. But we kept in touch, and this is really like basically a interpersonal interaction. And with my Palestinian colleague, for a while I was on soft money, and I saw that there were funding available for Israeli-Palestinian research. So I thought, okay, well, and I looked on a list of Palestinian colleagues in my field. I found his name, I emailed him, he answered me, and we became great friends. We've been working together for 15 years. So, but the thing is that beyond science, we realized that we have a platform. And we all very interested in, we said, the other thing that I wanted to show you is that we have now developed the algorithms for a very fast and efficient early warning system. We also work with Berkeley. So we realized that if we want to, we are setting up a very good early warning system, but if the people don't know what it is, or don't know what to do with the alerts, we've not done anything. So that has thrown us into education. And then we realized that it's not only education, because it's also on a lower level. We're aiming at high schools or the general public, but we have a lot of other issues of languages, but mainly culture. So What we're doing now is that we took an initiative that started in Europe at the ETH, and it's kind of very slow growing. It's called Seismo at School. It's basically an internet platform for high school kids for the physics curriculum dealing with earthquakes. And they have little games where they start analyzing earthquakes. And then we had the idea, because now if I go back, we realized we have a platform, and each of them is basically an independent unit. Each of them can identify and analyze earthquake. But of course, there is a huge value of working together, analyzing it together. So with my colleagues, we realized that if we put this platform, then we can put Israeli and Palestinian and Jordan kids analyzing seismic data and working together and comparing the analysis. Okay, so now what and the idea is to have a few centers, one in Palestine, one in Jordan, and actually we're building one in Tel Aviv University, and a network of high school around, with also the instruments, and having an internet-based education platform on earthquake, which fits in the physics and maybe geography curriculum. And now I just want to show you very quickly, we're just starting building it and developing it. So basically, the whole center, which I showed you the one that's been designing for Tel Aviv University, has three different modules. One is education, so there is a cluster of interactive stations where they can learn about wave physics, experiment, they can do their own earthquakes, all the really nice and things that they relate to, and it brings them to also a higher level of education. The second thing that we do is that we have a huge simulator. It's the only one in the world. This one doesn't work yet, but we have one we work with the ETH in Switzerland. They have one that already works. It's a platform of 8 by 8 meters on which we replay real earthquakes. So we train people, because even here, most people have not been through big earthquakes. They don't know. And they certainly wouldn't know what to do and how it feels. So we put them on that stage for about half an hour, and I'll show you. I think I have a little movie, if it works. Do you know if... I'll show you very quickly. This is the platform. You can put about 20 people. I mean, here there are just actually politicians. And we have huge screen. You can see how it shakes.
From the Department of Archaeology and Ancient Near East Culture, and for the past 4 years the Director of Excavation here at Mossad. I've been working here for the past 20 years, and my scientific heroes are the Monty Pythons. And you heard about molecules, and you heard about Mother Nature and soil and sediment, but we didn't speak about the human factor. And being the representative of humanity here, so to speak, I'd like to speak.
I'm also representing humanity.
So I'd like to share with you some of the insights of the future of the past, so to speak, and what we do here in the past several years, and why Masada is an excellent lab for learning about human activity 2,000 years ago, and why it's so relevant even towards today's science, human activity, and so forth. And when Professor Yossi Klafter, our president of the university, opened the center here for research of life under extreme condition, I came to him and said that this is the best definition basically for life at Masada, I mean life under extreme condition. And so for that we have a lab here which helped us just came back from Cambridge it was -9. I came from the Dead Sea, so that under extreme condition certainly works for him. Several years ago, I was asked to, an American president came to visit George W. Bush, and I was asked to accompany Professor Condoleezza Rice. It was a lovely tour, and I started the tour with her, the same I would like to start with you, quoting a famous American philosopher by the name of Donald Rumsfeld. And in 2001, he gave an unforgettable speech about the unknown unknowns. And he spoke about military intelligence, but he was referring to the fact that there are no knowns, that is to say, things we know, we know. There are also known unknown, that is to say, things we know, we don't know. But there are unknown, the thing we don't know, we don't know. I don't know if Rumsfeld knew what he was talking about, but this is the best definition of my profession, basically science. There are things we know, we know. We know there is a site by the name of Masada, due to the fact that a very gifted historian by the name of Flavius Josephus wrote 2,000 years ago about it. We know there are unknowns. For example, we didn't know where the tomb of King Herod the Great was located, or where is it, and several years ago it was found. But the greatest fun in my profession is actually what we don't know, and I hope I haven't lost you, but when we start an excavation, and we just ended one 10 days ago, there were a few surprises, and towards the very, very end, it's like you've been promised a gift when you come back, so hopefully towards the very end of the short tour I want to share with you, you all hopefully will be crawling into a cave, and I want to share with you the greatest discovery. It was not even published, so you will be probably the first to see it, but we found an inscription on the walls. It was there for 1,500 years, the past 1,500 years, and everyone missed it, so I would like to share it with you, so that's a sort of gift to the very end. So let's go straight up, 5 minutes walk, we'll take the cable car up. I know that all of you want to climb the snake pass, but as I've mentioned, you can buy the t-shirt Einstein Masada.
Please. אהלן. כן. אני רוצה שנשב מתישהו. כן.